Hello, I am Christoforos and I'll be presenting our work in relation to the multi-disease, multi-view and multi-center right ventricular segmentation in cardiac MRI challenge on behalf of my team. So for this challenge, we propose the Tempera network, a spatial transform feature pyramid network for cardiac MRI segmentation. For this challenge, our goal is to segment the right ventricle in both the short axis and long axis views in cine cardiac MRI scans. We achieve this by incorporating both views into a single network so that one view can improve the segmentation of the other. Specifically, we want to improve the segmentation accuracy of the short axis in the basal slice to the boundary between the ventricle and atrium, and the apex slice, so the slice at the end of the heart. This is due to the fact that the short axis slices are thick, making these boundaries difficult to identify. Hence, a slice along the through plane of the short axis, the long axis image, can help us localize better the ventricle. As we can see from the two images, the short axis is a stack of 2D images creating a 3D representation of the heart. On the other hand, the long axis is a single 2D image that captures the 4-chamber features of the heart. Traditionally, the left ventricle has been studied more extensively than the right ventricle, as it is associated with a larger number of pathologies. However, having structural and functional information of the right ventricle can also aid us in the diagnosis and monitoring of conditions. Thus, it can play an important role and can still offer us valuable information. Some examples are coronary heart disease, pulmonary hypertension, dysplasia, and cardiomyopathies. As we mentioned, the right ventricle has not been studied as much as the left ventricle. One contributing factor to this is that the right ventricle is more difficult to segment by both clinicians and automated algorithms. Some of the factors that contribute to the segmentation difficulty is that its structure varies a lot more than the left ventricle from patient to patient or pathology, as it has a more complex crescent shape. Additionally, its ventricular walls are much thinner, making it more difficult to distinguish from surrounding tissue. And finally, the right ventricle has heavier presence of wall trabeculations. Now that we defined our problem, we can move to the methods in which we will briefly go over our proposed model for the challenge. To be able to help the network, we do a set of simple pre-processing steps. We start off with resampling the images using B-spline interpolation, so that we have consistent resolution across scans. Specifically, for both the short axis and long axis images, we resample to a resolution of 1.25 times 1.25 mm in plane. And for the short axis, we resample the through plane resolution to 10 mm. Then we detect and crop a smaller region of interest of the heart. The resulting in-plane size of the images is 192 times 192 pixels. Additionally, we standardize the pixel values of the cropped images so that it has a mean of 0 and unit variance. Finally, we perform an affine registration between the short axis and long axis pairs, so that we obtain an affine matrix that maps the image space between them. Once we go through the model's description, it will be clearer why it is needed. In relation to data augmentation, we keep it fairly simple so we can focus on a model-driven solution rather than a data-driven one. So we randomly apply small degrees of in-plane rotations, in-plane anisotropic scalings, Gaussian blurring, and adding Gaussian noise. Now we can see an overview of our proposed model, Tempera. The network takes as input the short axis and long axis images, then we pass each single 2D in-plane slice from the views to our proposed feature pyramid that we will explain in more detail shortly. Following, we reconstruct the views such that we obtain again the 3D and 2D 3D short axis and 2D long axis images, which are then passed to their respective convolution branches to predict the right ventricle segmentation. Here, we also utilize another component, the geometric spatial transformer, which is a non-chainable differentiable component. It allows us to transform the short axis segmentation to the long axis image space by taking the affine matrix that was described previously. Thus, we expect to improve the long axis segmentation by incorporating spatial information from the short axis. Also, we can improve the short axis by allowing the loss from the long axis to backpropagate through the spatial transformer. Our model uses is scaled exponential linear units as the activation functions, and the weights are initialized using the Kant's method so as to maintain the self-normalizing property in the network. It is also optimized using Adam's algorithm and minimizes the combined loss of dice loss and focal loss. Our proposed multi-scale input-output feature pyramid that you can see in more detail here is designed to share features between the short axis and long axis views, and also between slices of the short axis. We expect that it can also benefit segmenting cases with pathologies which the network was not trained on, such as dilated right ventricle. We do this by passing each input at different levels of the pyramid and obtain the output at the respective output layer. As we can see from the two bottom components, practically this is achieved by including padding or cropping after each downsampling or upsampling layers, respectively. Now, let's look in a bit more detail at the spatial transformer. From the images metadata, we can obtain the spatial relationship between the short axis and long axis views. However, there can be some misalignments that can be caused by page movement between scans, for example. To address this, we use this initial alignment in an append registration algorithm that maximizes the meter information which is implemented in the simple ITK package. We treat the long axis image as 3D and do a 3D to 3D course-defined registration. Then the spatial transformer takes the affine matrix and applies it to the short axis image and resamples that to the appropriate long axis plane, as we can see in the image here. We evaluate our model with the data provided by the challenge. Specifically, 160 images are used for training, in which we randomly split it into 150 and 10 for training and validation, 40 provided during development, and 160 used for the final test of the model. The test set contains two pathologies not present in the training set, which are dilated right ventricle and tricuspidal regurgitation. We summarize our results in the following table and evaluate the performance based on the dice score and Hausdorff distance. As this work was done as part of the challenge, we are not able to compare our model against others yet when preparing this overview. We can see the performance on the development set and on the test set. During testing, there were some failures in the pre-processing stage, which should be attributed to fix. If we exclude those cases, we can see that our model is able to maintain similar performance on the test set when compared to the development set. We also visually evaluate the segmentation performance. In this image, we have two representative cases. In general, our model is able to accurately segment the right ventricle in both the short axis and long axis images. However, as we can see in patient 1, it occasionally undersegments in the short axis and specifically in the basal slices of the image. So, a quick recap. We just presented our Tempera network that segments the right ventricle in both the short axis and long axis images as part of the data challenge. It can quite accurately segment the right ventricle and has shown good generalizability to an unknown dataset with a different distribution from the training one. Our proposed feature pyramid gives the network the ability to identify and transfer relevant features between the short axis and long axis views. Furthermore, the spatial transformer is an effective way of incorporating prior spatial knowledge into any network. This even further helps it generalize to unseen cases. We believe further improvements can be made to our model. The next step that we will be exploring is the inclusion of the temporal information from the cines. Here, the spatial transform can again help us associate the cardiac phases between them. Thank you for listening. Any questions can be directed to the corresponding email.